Hello, and welcome to these lectures. Sorry that I can't be there, so I'm just pre-recording these, but I suppose that's the best I can do at the moment. Well, I'm going to be talking about really this lecture series is all built around the idea of us trying to learn how we would start to write an operating system from scratch, and the aim isn't really specifically operating systems or specifically programming. It's just really getting to understand the computer better, which will help you when you're doing high-level programming in whatever language. If you can get a firmer grip on what's happening underneath, what's happening inside the computer, how much of the stuff is done by hardware and how much is done by software, how much of what the computer does is handled by the operating system, what is the operating system, and things like that. By building up through this idea of writing an operating system, then we can really learn about all these other things. They kind of all tie together. So the idea is just to show you some very practical things, like how we can start to write low-level code, looking at assembly, machine code, then building up eventually into C. So here we go then. So, well, my name's Nick, by the way. And so what do I do? Well, I suppose I'm a computer scientist and a programmer. Recently I've been working in security, so all of these things are very relevant to the work that I do. Right, let's get started anyway. So the computer, if we think about what the computer is, well, most of us use a computer now for the work that we do. We press a button on a computer and switch it on, we wait a few seconds, and then we start moving our mouse around and logging in and browsing the web. But what actually happens, how does that system get started, and how is it built up? Well, really, I mean, the actual hardware inside the computer is very simple. The things it does, the actual theory of how it works is rooted in like Alan Turing's work, I suppose, like the idea that you can solve any problem by writing a computer program, and a computer program is something where you can define functions, and the functions can call other functions, and the functions can modify data, and the data that they modify can control how other functions are called and things like that. So you can really, by using this simple idea of calling functions, having conditions, if this, do that, else do this, you can build up very complex systems. But the hardware that supports that usually has a very small, relatively, instruction set. It can only do very basic things like add numbers together, multiply numbers together. There's a tendency now for the modern hardware to have more parallel processing. So although it still does the simple instructions like adding things, checking conditions, doing logic, then to get more speed out of the thing, then you tend to get like more parallel pipeline of instructions. I'll talk about this stuff later on, but anyway, the hardware is usually relatively very simple, the way that we interface with it, but it's the layers of software on top of it that give us all of the richness of using the computer. And of course we couldn't do the things that we could do if the hardware couldn't perform as fast as it does. Especially when you look at gaming and stuff like that. Gaming is always pushing the performance boundaries of the machine. Okay, so onto the computer. Well, if we want to understand how our computer works, then I've taken the approach here that we're going to start from looking at how it boots up, and if we can take control of it as soon as it boots up, then we suddenly enter into this very low-level environment that we're not used to when we're using high-level languages, where we have all these APIs of functions we can call to do draw windows, write games, all of that stuff. At the lowest level, even before the operating system starts, when we're booting, we have a very limited environment what we can do, but it's very useful without all of that stuff getting in the way. It's a very useful place for us to understand how to write assembly and how machine code works. So we're going to do that. So Well, firstly, how does the computer boot? So when I turn the computer on, it boots up. I know that I can install Windows or Linux or whatever else on my computer and boot it into that operating system. But how does it actually start it? The computer itself doesn't really, when it first boots up, it doesn't really know much about the hardware that's connected to it or anything like that. So, for example, when the computer boots without an operating system, it wouldn't be able to switch into some sort of 3D graphics context for playing games, for example, because the software required to drive that hardware is just not available to the computer. The operating system has to find and load all of that stuff. So what does a computer do? Well, it needs to be able to load the operating system from the disk. So it must have some capability of reading data from a disk. And this stuff is encapsulated in what's called BIOS, or some variant of BIOS, but I'll just talk about BIOS. So the idea of BIOS, which means Basic Input-Output System, is that the computer has some software written in a chip on the motherboard that can do some very low-level initialization of the computer to get it into a state where it can do some basic input-output, enough so that it can read the disk, read an operating system, and then start that bootstrap process of loading the operating system. The other things it can do are it can render stuff to the screen. So when the computer boots, we usually see it start in like a text mode, a simple text mode where we can see some console text. So that's also important that we can do that. So that's what it is, basic input-output. It's just a very basic form of input-output on the computer. And without that that initial software in the chip, we wouldn't be able to start the operating system. So we're going to look at writing a boot sector from scratch from using hexadecimal. So just writing machine code, which will really highlight how the computer works. But basically the boot process, how it works is when you look at, if you take the disk out of your laptop or whatever, and you look at the disk, at a very low level what you'll see is that it's just the way we interface with that disk at a low level is that we just read sectors from it, and a sector is a fixed size chunk of bytes that we read off at a time from the disk. Usually, I mean, they're slightly bigger now, I suppose, for performance reasons, but we often have chunks of 512 bytes, and that's a sector. And these map onto the surface of the disk if it's like a hard drive. If this is like a USB memory storage device, then these will map onto some part of the memory. But anyway, so we read sectors from the disk, and so BIOS is able to read some sectors from the disk, and then it's got to boot them. But the thing is that when you have disks in your machine, some of those disks might have data on them, and some of them might not have an operating system on. So BIOS needs to know whether it can run the code on the disk or not. And the thing with a machine is that there's no real differentiation between code and data stored in memory. It's what makes the machine so powerful, because we can mix code and data up. You can even write code that can write itself by writing to data that then runs as code. So this is very powerful, but it does mean that BIOS needs some way to know whether a sector on our disk is bootable or not, so that it can run that code, and then that will load the operating system. So what we have is there's a magic number usually that goes at the end of the boot sector on the disk. So, and all the boot sector is it's the very first sector on the disk drive, sector 0. So BIOS can loop through all of the disk devices. If I've got a CD installed, or I've got a hard disk, or I've got a USB stick installed when I turn on the computer, BIOS can loop through them all, read the first sector off them, check if it's bootable by looking if it's got a magic number in it. I'll show you the magic number soon. And then if it's got one, it will run that code. And once that code runs, that will do some more bootstrapping to load other code, usually using BIOS routines initially. And once that code is loaded, well, then it can start to boot the operating system. I'll talk more. The computer starts in different stages too, so the other thing that's important is that when your computer boots, it will start in what's called 16-bit mode, and this is to be compatible with very old x86 processors, because you might want to run an older operating system on your machine, and if your machine doesn't start in a state that knows how to execute that machine code, then it's not going to be compatible. So all modern processors, although the architecture's advanced and the assembly instructions, machine code instructions have been extended in places to better match requirements of software, they still all start off in this initial 16-bit mode, a very basic mode emulating an older processor, and it's the boot code from the boot sector and then the early operating system code that is responsible for switching up into 32-bit protected mode or 64-bit mode, and I'll talk about that a bit later on in lectures. But let's get on to some examples anyway. So what we're going to do is we're going to write a boot sector. Well, first of all, we're going to be working in hexadecimal, so it's important to understand why we need hexadecimal really. Often when you see, especially if you're new to programming and you see somebody writing numbers in hexadecimal, you often think, is there any need for that? Why has that person suddenly started writing hexadecimal code? So you can write numbers in hexadecimal or decimal, and they both mean the same thing. But the real reason for using hexadecimal is that if you look at this diagram here, it's much easier to convert between binary strings and hexadecimal than it is between binary and decimal. Internally the way the computer works is it's basically got on-off states which relate to digital signals, and so we see binary numbers like this one. Okay. Sometimes we have structures inside memory that use bits. We switch bits on and off to represent different properties of those structures. So the thing with binary is that it's very long-winded to write these numbers out. To write a program in binary, it would be very confusing. To write it in decimal, it would be confusing to convert it between binary to understand how it's represented actually in the system. But hexadecimal is a nice medium. Because it's base 16 and binary is base 2, it's much easier for them to convert between them. So if I look at this binary number here, if I want to convert that to hexadecimal, then I can just treat it as chunks of 4 bits. If you look here, we separate them out, and with those 4 bits, it's much easier to convert those into actual, I suppose, decimal numbers within less than the number 16. So for example here we see that it's not got the 1-bit set, so it's not got a 1. It's got the 2-bit set, so it's got a 2. It's got the 4-bit set, and it's not got the 8-bit set. So the number here is 4 plus 2, so we get 6. So we get 6 hexadecimal there. And the same for these, we can do that. It's much easier to convert this into a decimal number and just use that as a fragment of the final hexadecimal number than it is to remember all of these numbers. For example, to remember that this bit is like adding this number 32,768 to the final number to get the decimal. So basically it's much easier to switch between hexadecimal and binary, and that's why it's useful to know. And now what I'm going to do is go into a hex editor. I'm going to write a boot sector, and with this boot sector I'm just going to demonstrate that we can run it inside of a virtual machine. Now if I can run my boot sector code inside a virtual machine, then I can run it on any physical machine as well. And then I'll talk about using emulators, which is a much more easy way to write boot sector code, test it. So what are we doing now? So we're going to write the boot sector. So first of all, what I'm going to do is create create the boot sector file. Okay, all I've done now is create an empty file. It's got no bytes in it. If I just look at the size of it, okay, I think it's put 1 byte in it. So I've created that empty file, and now if I open that in a hex editor, I'm using ghex here, but you could use whatever you prefer. What I'm going to do now is write some hexadecimal numbers into this this file, and then I'm going to write this directly as I'm going to use this directly as a boot sector in a virtual machine to run this code that I write in here. What I'm demonstrating here is that the computer, all it understands is numbers, okay, and a program, as far as the computer is concerned, is just a sequence of numbers that it treats as opcodes, which are commands like jump or you know, for comparing numbers, copying data, things like that. It understands the opcodes, and then I can give like arguments to those opcodes, which are also encoded as numbers. The point here is that this isn't the most intuitive way to write code for a computer, but it's going to help us understand it. And we're going to look at, once we've done this, we're going to look at how we can write things in assembly that compile down into machine code, and then we'll build on top of that and look at C. So let's start off. So what I'm going to do first of all is just write this boot sector. So in here I'm going to type some bytes. These are hexadecimal numbers. Okay. And now what I'm going to do is, because I told you the boot sector, BIOS expects to read a boot sector that's 512 bytes long. So what I've got to do is make sure that this file is 512 bytes long. In hexadecimal, I'm looking at this offset down here, which is telling me the current byte in the file that I'm editing. And if I get this to 200 in hexadecimal, then that will be 512 decimal. Okay, here we go. So what we've got there is 200. Actually, what we want 1 byte less, because this byte here is the 512 byte. Right. Okay. Let's look at this. So I've written some things in here, and what this represents here is an x86 machine code instruction to jump to itself, which translates to an endless jump. So it's going to jump to its own address, and then it'll do the instruction again, so it'll just keep jumping. The reason I've done this is because we don't want to write any well, we don't want to write much code in hexadecimal, in machine code, but we do want to make sure that we can see that it's working. And one way of making sure that it's working is to throw the computer into an endless loop, so that it will just run, it will just hang there, but it won't fail or anything like that. Okay, so let's carry on. So if you remember, well, actually, let me. No, I'll do this first. So if you remember, I said that BIOS, when it loads the boot sector from the disk, it needs some way of differentiating between a block on the disk that's just data and a block on a disk that's bootable. So it looks at the very end of the first sector on the disk for the magic number, and the magic number is just a well-known number that it expects to find there. If that number's not there, then this sector won't be treated as a boot sector, and the code that I've written at the top won't boot. For now, I'll just put the magic number in, but the magic number looks like this. Let me just delete that. Okay, so that's the magic number. Oh, good. Right. So what have I done? I've just written a boot sector in machine code, and I'm going to save that. The idea of this is it's supposed to be tedious. That's why it's taken ages. So save my boot sector, and now what I'm going to do is I'm just going to run a bit of code to turn that boot sector into an ISO image. An ISO image it's an image file of a CD-ROM, and we can use that to load it into a virtual machine. So how I can do that, don't need to worry too much about what I'm doing here, but basically I'm just turning that boot sector into an ISO image. Okay, so now what I've got is I've created this file called BIOS.iso, and this is just, for now, it's just got my boot sector in it that just has that endless loop. So what I should be able to do now is to load this as though it was an operating system installation disk into a virtual machine, and it should hang there because of my jump instruction that I wrote to machine code. So let's do that. So I'm in VirtualBox now, which is an open source free VM virtual machine system. Now, and what I could do, that ISO file that I created, I could take that, write it to a CD-ROM, and stick it in my computer and reboot it and boot it on my real computer. But it's very convenient now to use virtual machines to test things like that, and it works in the same way. So I'm going to create a new virtual machine, and I'll call it test VM. It doesn't matter what operating system it is because I'm using my own little operating system anyway. Okay, so I'm just creating a standard VM here. Okay, and now I'm going to start my VM. We'll just ignore that. What you'll see is that my virtual machine has no operating system, so it's pretty much, this is the equivalent of when I've bought a new computer that's not got an operating system, and I've just switched it on and it's telling me there's nothing to boot. Okay, so what I'm going to do is just close this down, and I'm going to insert that ISO file that I created with my boot sector code on, as though it was a CD-ROM, into the virtual machine. So if I go to where I want to go, second, power of a machine. I want to find a virtual disk. Oh, here it is. So BIOS, which I just created, and I'm going to open it. Okay, so now inside my virtual drive on this virtual machine, I've got my ISO file that I created, and now I'm going to power the virtual machine on. And what's happened? Look, so well, we've got a blank page, but this is good. Okay, because what this is doing is, it's not said there's no bootable disk on the machine. It's picked up my boot sector that I wrote, and it's booted it, and it's gone into an endless loop. So this is probably one of the fastest loops I can run on this computer, or if I install it on a physical computer, it would be the fastest loop I could make, because it's running, there's no operating system, it is the operating system, it's running at the lowest level, it's just running a loop. If I wanted to heat up my office, I could probably do something like this, and it was just looping around, so the CPU is just spinning around and around as fast as it can. We're going to look later on how we can write strings to the screen and stuff, and we're going to build that up. But that's good. Now let's just to play around with that idea some more. If I take my if I edit that boot sector again, and what I'm going to do is this magic number at the end, I'm going to change it slightly. So instead of having that thing, I'm going to change it to 5F. So it's now not got the magic number, so let's save that. Okay, now I'm going to just make that boot sector again. Yeah. Let me just recreate that. Okay, so I've created that boot sector again, and now if I power on my VM, okay, so it's still using the, let me just change that, it's still, I need to just remove this. So all I'm doing now is, in fact what I'll do, I'll demonstrate this in, I'll just explain how we can use emulation to do this stuff. So I was using a virtual machine there, which is very useful. Often a virtual machine is good for when you're actually running a real operating system. But when you're writing this kind of low-level code, an emulator is often more suitable because you can quickly run the emulator. An emulator allows very powerful debugging of very low-level code. And just to explain the difference between a virtual machine, so a virtualization and emulation, is that with virtualization, the software such as VMware or VirtualBox tries to run as much code natively on the host processor from the guest operating system as possible. Although in some cases it can't do that, because like when you switch into the operating system or you call hardware CPU instructions, you have to emulate those. So a virtual machine tries to optimize for like practical usage, so using the CPU directly, whereas with emulation the software actually pretends to be the CPU and all the instructions run within the emulated environment. So when it's calling a CPU instruction, it's actually just simulated like in some C code or something. So if I call an assembly instruction to move something into a register and then add a value to it, that will translate to maybe some C code in the emulator that simulates the register as a variable, and when it adds one register to another one, it just uses an add, a high level add function. So the thing with emulation is that you can emulate different computer architectures on your machine. So you could emulate different, like an ARM processor or a RISC processor on a like an x86 machine. So let me just run my boot sector again. So what I'm going to do now is run my boot sector that I just wrote in a thing called QEMU, which is it's quite a nice emulation. So this runs just like an actual PC. So I'm passing it my boot sector that I created, and we'll see what happens. Okay. So here what it's doing is it's trying to boot from I passed it the drive to boot from, which was just my boot sector, and it's saying it can't boot from it. It's saying no bootable device. It's going to retry, and it's just trying things like while it's looking for DHCP, it's trying to do like a network boot, looking for a host on the network that it can boot from. But there's nothing there, so it can't boot. So if I kill this process, and then in my hex editor, if I put this back to the magic number, there we go. So I've added the magic number now to the end of my boot sector. and I'm going to try that again and see if it boots. So it's saying it's booting. Okay, this is similar to VMware, but this is using QEMU now, and it's basically gone into that loop again, so it's working. So what that showed was that if I don't have the magic number in my boot sector, so the first sector on the disk that I give to the virtual machine or the emulated machine, then it doesn't try to boot the code, it doesn't run. So what we've got now is we've written a very low level piece of code for the machine. In fact, it runs directly. There's no operating system running when we run this code. The code that we run is the equivalent of the operating system, or the operating system bootloader. What we're going to do in the next lecture after this is look at how we can start writing stuff in assembly, and we're going to write some boot sector code in assembly and start to build up then until we can look at how we would start to write some bootstrapping code to load C and all of that stuff. So so there's our boot sector. So just to look at that again, if I look at my boot sector, so we just wrote those these values into here, which represented the machine code instructions for a jump. Like I said, the computer just understands numbers. When we write in high-level languages like C or even assembly, and we use things like if and function, call a function, stuff like that, plus equals, whatever. The computer doesn't understand that stuff. That's just for us so that we can easily differentiate between instructions, and usually the compiler or the assembly will then translate those things that we understand into low-level machine code instructions. And if you take any compiled program, you can always edit it in a hex editor, and you can look at the assembly instructions inside it. So this was our jump here, and at the end we had our magic number all the way down the bottom. Okay, I've gone way past it there. Where are your magic number? There it is, the BIOS magic number. Just ignore these other bytes at the end here. I had to extend this beyond 512 bytes when I was creating that ISO image. That's why there's these other numbers. But the boot sector is from here all the way up to here. So we created a boot sector. Now, just before we end this, what I'm going to do is, which is quite interesting, is to look at a real life boot sector. So on my machine, when I switch my machine on, it boots up, and I've got this machine configured to run, it either can boot into Windows 7, which I use occasionally, and Linux. And so what I'm going to do is look at the boot sector on my disk that starts all of that off, to see how that compares with the boot sector that we wrote. So without this boot sector, my computer wouldn't start. If I deleted this boot sector, I'd have to put it back somehow, otherwise I wouldn't be able to use my machine. Let's see what's inside it. So, well, first of all, I need to just clear that. I'm just going to run this command, which it uses this DD Linux command, which is basically just for copying bytes from one file or device to another. And what I'm doing here is copying this device here, dev SVA, is my main hard drive in my machine, and I'm saying use this as the input, and as the output just write to a normal file. And I'm saying copy sectors of size 512 bytes long and copy one of them. So basically this command is just saying copy the very first sector from my hard disk into a file, and then I can then I'm going to look at that in the hex editor. So let's do that. So I've copied it. Now if I run ghex on this, so I'm now looking at my real boot sector from my machine. There we go, look at that. So, well, we've got lots of stuff in here. Now from the stuff I had showed you before, we know now that much of this stuff at the start will be machine code opcodes and their arguments to do jumps and stuff like this. But I don't know from looking at this, without disassembling it, which we can do easily enough if we want to. Without disassembling this, it's harder for me to differentiate between what of this is code and what is data. Now if you look on this right hand side, you'll see that there are some recognisable text in there, so these are definitely data and not code. But anyway, it doesn't really matter. The point is that within this boot sector on my disk, it's got a bit of code that does something, and it's got some data in there too. Now this stuff here, so it's mentioning grub, so grub is a bootloader, and it's the bootloader that I use to boot my machine. So when I set up this machine, I used grub, which is this software, to create a bootloader to allow me to boot between Windows and Linux. And this first sector can't contain the whole of that bootloader, because grub is much more complex than that. But what it can do is have a bit of code that can do enough to load some more code from the disk. Because remember, BIOS only loads the first sector, whereas grub spans a few, probably kilobytes I think. So it'll load some more sectors from the disk, and then with those it'll have some more advanced code that knows how to load Windows or Linux. Well, if we look at the end of this boot sector, we see our magic number there, 55AA. If I took that magic number out and then rebooted my machine, I wouldn't be able to boot it up. I'd have to boot up from some other, like some CD or something, and then edit my boot sector and put that magic number back in to make it work. And also in the boot sector, when you have partition drives, the end of the boot sector, probably somewhere around here, although I can't be sure, but it'll be somewhere towards the end of the boot sector, it'll have information about the partitions to say that a disk drive that's so large has been split up into separate partitions. Usually you can have 4 partitions listed in there, and if you need more partitions then it has to reference another sector that's got more stuff in, but we don't need to worry about that now. But basically the boot sector has got some code in it for initiating the boot after BIOS loads the boot sector, and it's got some data in there, usually for partitions or for something else, and the magic numbers at the end. So that's everything really. In the next lecture we can look at writing some boot sector code in assembly, and it's a really nice way of getting more familiar with the low-level side of computing. Not because we want to spend all our time writing in assembly, because we don't. The problem with writing in assembly is that okay, you can optimize things, but you can only optimize them for a particular processor. So if I then want to run my assembly code or my program that I wrote on another architecture, you know, like an ARM, like a tablet, or a phone or something like that, I'd have to rewrite it in the assembly for that particular architecture. But by understanding assembly and machine code, how the computer works, how it boots, we can really have a better understanding of how an operating system works, and also understand how our high-level code that we write works underneath, so that if we do need to optimize things or whatever, then it's useful. And this is particularly interesting when you come to writing in C. And if you start writing in C with a background of writing in Java or some scripting language like Python or something like this, then you always find it difficult to grasp the pointers and that side of memory referencing, because it feels strange to talk about memory addresses in a high-level language when before that you didn't need to worry about it in Java and things. Whereas if you come at C from a low level, from assembly, the addressing and the pointers make a lot more sense. So we're going to try and look at it that way. So we'll leave that for later on anyway. But thank you for listening, and I'll be back with another lecture soon. Thank you.